Welcome everyone to this week's Western Hemisphere Virtual Symplectic Seminar. We're very happy to have Luya Wang from UC Berkeley talking about a connected sum formula of embedded contact homology.
Thank you, Catherine. So today I'm going to talk about a connected sum formula for embedded contact homology. I'll give some motivations and background first, and then I will give an overview of embedded contact homology, and then I will show you a rough sketch of the proof of the connected sum. So the motivation besides connected sum is a natural question. There's in linearized contact homology, this formula has also been studied by Bourgeois and Van Coort. And if you're familiar with any of the three theories that are isomorphic, so this is ECH is isomorphic to monopole Floer homology, which is isomorphic to Hager Floer homology, the plus version. Right, so if you're an expert, you can probably already guess what the punchline is, but I hope you'll still stay with me. So this is work by Taubes. This is work by Luhan Taubes. And this is by Kalingajini Honda. So it's possible to show the connected sum through these big isomorphisms, but I will give you a chain level description. And then, okay, other motivations, you can study other contact surgeries, as well as give a chain level description. That's usually used for other applications. Okay, so now I give you a overview of embedded contact homology. So ECH is a three-manifold invariant that takes the input of a contact three-manifold, Y, and associate to it a bunch of choices, which will be the ECH homology will be independent of, but so let's look at the choices we're making. Oh, sorry. So we pick a non-degenerate contact form, and so given the contact form, we can associate a unique rate vector field. And from the rate vector field, we get a bunch of rate orbits. And the ECH chain complex is generated by these so-called orbit sets, which are just tuples of gamma I and mi, where gamma i's are underlying simple orbits, and mi are positive integers, which counts the multiplicity of such orbits. And there's a technical assumption that if gamma I is hyperbolic, meaning that the linear residue map has real eigenvalue, then we require mi to be equal to 1. So we can't multiple cover a hyperbolic orbit. Any questions on here so far? Please interrupt me if you have questions. So ECH differential, to talk about ECH differential, I first need to tell you which symplectic manifold we're in. We're in the symplectization. So this is familiar in a lot of the stories. And we fix a generic symplectization adapted adapted almost complex structure. This is just saying it has to be R invariant J sends the S direction to the rape direction, and it fixes the context structure, rotating positively. So ECH differentials counts ECH index 1 J holomorphic curves. So it can have multiple asymptotic ends and multiple genus. And it's also possible to have these trivial cylinders. But I will talk about those, maybe I elaborate a little bit more here. So I will tell you what, roughly speaking, what ECH index is. I can't spend too much time on it. Well, I can spend too much time on it, so I will limit myself to half a page. So this is a topological index. And it involves terms C tau, Q tau, CZ tau. So I fix the trivialization of the context structure over the Rabe orbits. I can always do that. And these, so the C tau is a relative first string class. So roughly speaking, it measures, well, okay. I pick, given a relative second homology class, I find a representative and I pull back using this representative of my context structure, and I pick a generic section of this that's non-zero and non-winding with respect to the trivialization, and I can just count the number of zeros inside. And Q tau is the relative intersection pairing. Similarly, you pick specially chosen representatives of your second homology classes, and these are embedding around near the boundary, and you count intersections inside. Of S with S prime. And let me say interior. And then Colley-Zener index, I think people are familiar with this, is roughly speaking measures the rotations of the linearized return map. So why is ECH index? So ECH index is just adding up all these terms. Well, CZ, you have to be careful how you add it up with all the Rabe orbits, but roughly speaking, it's the sum of all these terms. So why is ECH index useful? It gives us topological control of low index curves. When ECH index is 0, we know our curve has to be a bunch of trivial cylinders. When ECH index is 1, it's trivial cylinders with multiplicities. These are so trivial cylinders with multiplicities. Plus an embedded ECH index 1 and Fredholm index 1 curve. And index 2, if you add the further assumption that your positive and negative ends are ECH generators, then you get a similar statement with the ECH index 1 curve. So, except you, I guess, put this equal to 2. Okay, so that's a very quick overview of what ECH index is. Now I need to tell you a little more structures on the ECH, which will be useful for the connected sum formula. First is a UMAP. The ECH UMAP is a degree 2, -2 chain map on the ECC complex defined by counting ECH index 2 curves passing through a generic base point. Let's say 0z cross R cross Y. And there's the action filtration, which is given a orbit set gamma, which is the sum of mi gamma I. This is defined to be the sum of all the actually integrated over the orbits. This gives you a filtered ECC complex Y lambda J, and it's actually shown that this complex is independent of J, so I can just get rid of J. And then for the audience more familiar with SFT, so ECH curves can have higher genus and any number of asymptotic ends, top and bottom. And what I have been surprising is that we're really counting currents instead of curves. So in particular, the branch, we don't keep track of the branch information. The pair of pans with one branch point is as current, the same as the double cover of a trivial cylinder. Okay, and just a few notes on why ECH is useful. So it's good at answering questions in RIB dynamics. You have the Weinstein conjecture by Taubes, and it tells you existence of RIB orbits and the orbit. And then you have the Arnold core conjecture, tells you the existence of RIB chords. And for ECH, ECH is also used for obstructing symplectic embeddings. These are, there is a quantitative invariance associated to ECH. I see these ECH capacities, and they're useful. They're monotone under symplectic embeddings, so they can obstruct symplectic embeddings. Okay, so that's an overview of ECH. And any questions before I go into the connected sum? Okay. So I pick a particularly simple simple model for my connected sum, contact connected sum, which is the Weinstein one-handle model. So I consider R4 with the standard symplectic structure, and I consider the hypersurface cut out by f equals to x squared plus y squared, z squared minus w squared equals to 1. So this is on hypersurface. And I pick the Liouville vector field x equals to x partial x plus y partial y plus z partial z minus plus w partial w. And from this, I get the explicit description of what the contact form is like. So W. And from the contact form, I get a ray vector field, x partial y, y partial x, plus z partial w, plus w partial z. So from this description, you can see that there's, this is the only orbit, and it's actually a hyperbolic orbit. I'll denote it as H, in this connected sum region. And if you look at the contact structure restricted to this H, it's just partial Z, partial W, and this is actually the trivialization I will pick over this orbit, which is very convenient. Okay. Maybe this is also a little fast. Are there questions regarding this model? Okay, so this is a topological, well, like this is a contact geometric model. but I need to tell you what the almost complex structure is when on the symplectization, since I will be studying differentials in the symplectization. So this is a theorem. Well, this is studied by Fish, Sifri, and DiPaolo Salama, I think. So the statement is that given any compatible J, there exists a compatible J prime agreeing with J outside this connected sum region. And in the connected sum region, there exists a pair of embedded disjoint pseudo-holomorphic planes. Let me just say, okay. Let me call them Pn and P south. They're both asymptotic to this special hyperbolic orbit H. Yeah, and then they project to the northern and southern hemisphere. So it's a very nice picture of what happens in the connected sum region, R cross S2. This S2 is the connected sum S2. So given these two planes will help me study the connected sum formula. And the claim is that these two planes actually has Ech index 1, although I will not calculate it, but it's not too bad. And they do contribute to my Ech differential of the connected sum, but they cancel each other, especially if I take a Z-mod. Let's just say I take a Z-mod to the coefficient. Okay, and a little bit of remark is that we can perturb these J to be generic outside of R cross S2. And for these planes, we have ultimate transversality. So if you're worried, don't worry. Okay. So now I will tell you a little more about the correspondence of Rayb orbits. So this will give us a vector space level description of what the ECC complex is. So first observe that given any action, any real number L, one can find a radius RL such that every orbit intersecting S2. So this S2 has radius RL, and any orbit intersecting it has to have action greater than L. So there exists such a radius. And this is just a compactness lemma. And therefore, given any L, we may find RL as above, like here, such that the ECC complex, filtered ECC complex of L. So you're just throwing away all the orbits with action larger than L, which is throwing away all the orbits that passes through this S2 region. So this one doesn't contain orbits crossing S2, except for of course, the small hyperbolic orbit H that's lying inside S2. So this observation helps us decompose our ECH complex on the vector space level to orbit sets that doesn't contain the hyperbolic orbit. and orbit set that contain orbit sets with a hyperbolic orbit. So both of them are just ECCY1, tensor ECC Y2, Y2. So you're just adding all the orbit sets together, taking all the combination of the orbit sets. And this is, as a vector space, the same as home of U1, tensor identity plus identity, tensor U2. I need to tell you this where this chain maps goes from, it maps to. So this map is from ECC Y1. You can think of it as the disjoint of Y1 disjoint U2, Y2, which is the same as ECC Y1 tensor ECC Y2. So the U1 plus tensor identity plus identity tensor U2, this map goes from this complex back to itself. Okay. So yeah, on the vector space level, I identified these two complexes. So I now need to tell you what the differentials look like here. From now on, I will suppress the action L, but I would just assume that I don't need to worry about orbits that pass through the S2 region. Okay, so I write my differential in the connected sum in terms of orbit sets that, of differentials that go from C0 to CH. So this in particular means that orbit index 1 curves that has positive end with all the hyperbolic orbits and the negative end with the hyperbolic orbit. Okay. So I just organize it this way. There's no content here. Okay, so the goal is to study, to understand all these differentials. Oh no, sorry, my pen is out of battery. Do we have questions before while I charge my Apple Pen?
I had a quick question. So am I allowed to take Y1 equals Y2 here? So like a self-connected sum?
Yeah. So, yeah, you can do that. But you can also, if you want to do self-connected sum, you can also just connect sum with an S1 cross S2, whose ECH you know.
I see.
Okay. To understand all these differentials in terms of the previous differentials in Y1 and in Y2. Okay, so first, let me show you a useful non-crossing lemma, which says if you have a curve whose asymptotic ends are in the original Y1 and original Y2, then if it crosses this region foliated by the planes, then these curves can't exist. This is a quick intersection argument. So essentially, okay, so I need to explain what this is. So Q tau is the relative intersection that we see. I'm not actually going to prove it, but this is just the idea, because you have, if you cross this region, then you cross with one of the planes, and then you have positive intersection that is greater than 1, but then you assume these orbit sets are just disjoint from the connected sum region. So that's the contradiction. So no crossing tells you that you can't have curves that cross this region. So you can just, now you're left to consider curves that are entirely here or entirely here, or they can have asymptotic ends on the special hyperbolic orbit that we added in the connected sum. Okay, and okay, the corollary of this no crossing.
Luya,
yeah.
You have a question in the chat from Yuan Gao.
Okay.
how does the decomposition into C0 plus CH look like on the tensor product after identification?
Tensor product. Tensor. I don't think I really on the tensor product. I think maybe there's a confusion. So C0 is one copy of the tensor product. CH is also one copy of the tensor product. Maybe does that answer the question or? So the cone has two copies of this oplus. Okay, thank you. Sorry, this is a little messy here. Thank you for your question. So the no crossing lemma tells us that this is just partial 1 times identity plus identity tensor partial 2, where partial 1 and partial 2 are the original differentials. Being y1, similarly for y2. Okay. Now let me go back to my blue. So now we understand what partial 0, 0 is like. So this term we understand, and let's discuss what these two terms are like. So these are the differentials with the positive asymptotic end at the special hyperbolic orbit. Okay, the proposition is that any embedded Fredholm index 1 connected curve with a positive end at in CH, which again is the orbit sets that has a hyperbolic orbit in it, and negative end the C0, which is the orbit sets, which consists of the orbit sets with all the hyperbolic orbit in it. So any curve that looks like this is either the northern hemisphere or the plane or the southern hemisphere plane. Again, this is by a similar argument on using intersection positivity, as well as the fact that there are two such planes, and you can study the asymptotic behavior of them. So I also won't go into the detail here. This is greater or equal to 0. So once you have this proposition, you know this differential is just 0. So in linearized contact homology, this statement is relatively simple because your positive end consists of one, that have if it only has H as a positive end, you can just make this hyperbolic orbit of action very small, then you don't have these things. And here it's a slightly more delicate argument, but you also have it. This is also 0. And regarding orbit sets that have both positive end and negative end landing on the hyperbolic orbit, the proposition, you already see it here, is that any embedded Fredholm index 1 curve with positive ends in CH and negative ends in CH has to contain a trivial cylinder over H. Okay, and again, this similar argument using the two families of planes bounding H. And this will tell us that you can write your differential of differential that goes from CH to CH as such. So you get rid of one, you get rid of this H, and then you do the usual partial 0, 0, and then you add this H back here. All right. Okay, so in summary, we know all these differentials. And again, the partial 0, 0 is just partial 1 tensor identity plus identity tensor partial 2, but now I'm just identifying them, and this is easier to write. So I'm going to write it like this as partial 0, 0. But we know what they are, these partial 0, 0. Okay, so what about this term that's left?
Oh, Luya, could I ask a question?
Yeah.
This H that the two pseudo-holomorphic planes are asymptotic to, can you say again a little bit more about it? Like how you find it?
Yeah, so that was
sorry to make you go back.
Oh no worries. That was the hyperbolic plane, hyperbolic orbit that we had to have while we did the Weinstein one handle attachment. So this is the equator of the sphere. And then I can make my model very small. So the radius can be very small. So this action of H can be very small. And what else? Under my trivialization, CZ is just 0. I don't know if that helps. And then the index is, well, the two planes has index 1. So the H has grading 1 in ECH. What else can I say? Yeah, does that help?
Okay.
Can you think of
yeah,
it as a
I
very
think
small
so.
hyperbolic orbit?
Okay.
That's the only thing that you add. You have extra in the connected sum.
That makes sense. Thank you.
Can I ask a question?
Yeah.
So what do you mean by 1 over H in this corollary?
Yeah, so like if I look at this orbit set, like let's say alpha 1, alpha 2, H, then 1 over H, I'm just picking out alpha 1 and alpha 2. I get rid of this H.
Okay, and then you and after taking the differential, you add the H back.
Yeah.
Okay.
Okay, so we're left with to study this partial 0H. So these are curves that go from orbit sets without the hyperbolic orbit to an end, negative end on the hyperbolic orbit. Blue. They come, okay, so the punchline is they come from U maps. In the closed manifold. And there are two ways to see this. I guess the more natural way is you consider a base point P on the moduli space, and the moduli, sorry, base point P and the moduli space of index 2 curves passing through P. So this is just the usual definition of the U map. And then you move this P onto one of the planes. Doesn't matter which plane you move on, let's say P south. And then, okay, then move P on PS, P south. And then you consider all the possible limiting buildings. And then if you use the intersection argument again, you see that these are the only possible configurations. Maybe you can have branched cylinders here, but you will have that on the top level, right? You have to have a negative end appear on H appearing. And then more precisely, well, actually, I'm not going to talk. Well, yeah, more precisely, consider the moduli space of index 2 curves passing through the interval that is Z1P union PZ2. So Z1 and Z2 were originally something on points Z1 and sorry, Y1 and Y2. And right, and then you consider the boundary of this, then you get this appearing as one of the boundary components, and then the others are something like K partial K, which I will not discuss, but I will discuss in the observation too, because they also appear. So instead of considering this limiting building argument, you can just consider the change of base point chain homotopy given in the original ECH. So if I have base point, I change base point, I have Z, originally I have Z, now I have Z1, then these two U maps are actually related by partial K plus K partial. So this is proven by considering if you're given an embedded, so I'm defining what this K is, given an embedded arc from Z to Z prime, so I call this eta, we can define K define a chain map on ECC complex by counting index 1 curves passing through eta. So you're counting ECH index 1 curve that passes through eta, you still pick out a 0-dimensional moduli space, and you can still count K. You can still define K. Okay, so this is already done by Hutchins and Taubes, and they show this K is, yeah, I mean, it's 0-dimensional, it's compact. And so what I do is that I observe the only index 1 curve. Oh, I already have the curve here. Curve having a positive and at H passing through this point P that I picked to be on the southern hemisphere is P south. So by the previous, well, previously I showed you if I have a curve low index passing through, sorry, not passing through anything, but it has positive n at H, then it has to be PS or P north. So now I just require, if I just pick the, give the extra condition that it has to pass through a point on the southern hemisphere, then it has to be the southern hemisphere. So similar to the above meaning this chain homotopy, we define a map K prime by counting, again, index 1 curves passing through Z1 P union P Z2. So I am really just subtracting these planes out of the original K. So the K map counts all possible things passing through Z1, Z2, and K prime, you get rid of this P point. So comparing with the previous K, we get U, Z1, connected sum, Z1. So this is the U map in the connected sum, counting curves passing through Z1. minus U connected sum V2 minus. Okay, I'm doing Z mod 2 so that these cannot be plus, but okay, so 0 is equal to, so 0, 0 means I'm restricting to only counting the curves going from orbit sets without the hyperbolic orbit to orbit sets without the hyperbolic orbit. Okay. Plus K prime 0, 0. Okay, the proof is very simple. You just compare, essentially you're just comparing the difference between curves that, the curves passing through this the whole interval versus curve that cannot pass through the P point. And yeah, and then that's these planes, which I denote as 1 over H. You're just capping it off. Okay, so this established a correspondence between index 2 maps, index 2 curves in the original 3 manifold, passing through a base point Z1 to index, I guess this is Y1, adding H. The differentials, so index 1 curves that having a negative end at the hyperbolic orbits. But the precise statement is that you need to add in this partial K plus K partial. Okay. So the U map and the differential with H as a negative end. All right, so finally, I gave you the chain homotopy equivalence between my cone complex and the connected sum complex. So this is given by H K prime 0, 0, K prime I defined to you before. H. All right, so the proof is that this is lower triangular and it's isomorphism on the vector spaces. So I just need to show you, suffices to show that F is a chain map. i.e. F part cone is F. Okay, so this amounts to just check these multiplication of 2 by 2 matrices. And it's very nice that they all work out. So yeah, you just multiply them out. Okay, let's go through them. Identity times partial 0, 0. Okay, these two are the same. And then you don't have these terms by the previous lemma. So this is good. And this is 0. It's also good. So this equation, all right. So we know by the chain homotopy, the change of base point chain homotopy, you have, this is H times, so you're using this equation, which is 1 over H partial H0 plus partial K plus K partial, but these are, and everything is restricted to the here. And then you just multiply it out. So this term cancels with this term cancels with this term, and this term cancels with this term. Because another thing you need is partial HH times H is equal to H partial 0, 0, which is also a term that we had, equation we had before. And then the last one is just exactly this equation. So this is also satisfied. And then this is our chain homotopy equivalence between my cone complex and my connected sum complex. And that's the end of my talk.
Thank you. Are there any questions or beyond the ones that were already asked? Go ahead.
Yeah, can I ask a question?
Go ahead.
So at the beginning you say there is equivalence between the embedded contact homology and this monopole floor homology, and is this connection formula compatible with these isomorphisms?
So I think a group was working on this connected sum, but I'm not really sure what. So the version corresponding to mine, I'm not sure if it's written down, but I think the experts know what it is. I should ask them to see their draft out or something. Yeah, I don't know. I just haven't seen this. I think it is. So this clone is a derived, you can understand as a derived tensor product. And so they should be also getting that, I think.
Okay.
Any other questions?
Yeah, I do.
Go ahead.
No, please go ahead.
Yeah, this question was asked before, but I think, well, there are different ways to understand the question. So I want to ask it again. So if you take a single 3-manifold and cut out 2 balls and then attach a 1 handle, so that's what one considered to be like a self-connect sum. So there's some hope of using related ideas to understand what happens to various kinds of contact homology of that.
Yeah, and then I think on the contact manifold level, it's just connected summing with an S2, 1 cross S2.
That well, it's like, I'm not sure because that you're oh really? Oh, you're saying that's topologically the same thing. Oh, all right, never mind. All right, so I didn't understand what you said before. Thanks.
Oh yeah, sorry, I said it really fast.
But so related to that, I was kind of wondering, so it seemed like all the techniques we're using should also kind of work with filtration. So I was wondering, like, can anything be said about the ECH, the ECH capacities of a connect sum? And so in the self connect sum case, then you would have to start worrying about the size of the belt sphere and things like that. But
yeah, I will. I was working on this and then I had to finish it. So yeah, that's one should be able to say something about. So the chain level thing should be able to say something about the contact invariant as well as the ECH capacities. But yeah. Oh wait, sorry. Are you asking still on the self-connected sum or the
or just connect sum in general? I was just curious because it seemed like I don't quite see what the naive formula could be because it has to sort of depend at least to some extent on the geometry of the connect sum. It seems like I don't know if I could imagine a formula that just involves the ECH capacities of each piece or something. I was just curious.
Oh, so I would guess it's the max of the 2 things because you also have this non-crossing. So whatever C1 achieving class you have here, the guess is that you are summing up all these orbit sets. So in the case of S3, you have like U maps. So you have U maps. So these are like the U map becomes, let's say this is the smallest elliptic orbit, and this is the other smallest elliptic orbit. And then under this connected sum, they both, so partial E1 plus E2 will still give you 0. It's still a cycle. And so I would expect this to be the C1 generating the energy of this orbit set to be the C1 achieving orbit set in the connected sum.
Yeah, you could probably make some precise sense of the question by considering some limit where the balls where you do the connect sum get arbitrarily small. So you can imagine some kind of singular connect sum 3-manifold and define its ECH spectrum to be the ECH sort of the limit. The ECH spectrum as the size of these balls goes to 0. So then I think that's then a well-defined question. Maybe it depends on the direct limit, how the direct limit works.
Yeah, the direct limit.
Well, maybe can I ask a question?
Mhm.
Thank you for the talk, first of all. I don't have something very articulate, but it seems like what you're doing when you're relating, when you're talking about how the U map relates to those curves which have negative asymptotics to the hyperbolic orbit.
Mhm.
It seems like you're giving a proof, like you're proving that the sutured contact homology, when you remove a ball, is the same thing as the cone of the U map, which I don't know if it's
Oh.
formalized. It was formally written down, but can you go back to talking about some of the details there? Because my understanding is there should be some kind of like elliptic orbit which gets canceled and has to be.
Yeah.
I guess when you're working in a ball, then you can like create a canceling hyperbolic and elliptic, and
Mhm.
Right. I'm not quite sure if I have a good question.
So the connected sum, another model you can take for the connected sum is like what you said. You take y1 and y2, you take ball outside of each, but then you get concave suture manifold for both. So you need to turn one of them into a convex suture manifold, and then you can glue them into the usual connected sum. And I mean, topologically it's the same picture, but the somehow the pseudo-holomorphic curve picture around this neck is not as I didn't understand what it was. So I instead took the Weinstein one handle. It's way easier, but I think there's a relation. There should be a relation between the suture picture. So if you just take one side, y1, take out a ball, and then you turn it into convex, that's the sutured ECH. Define it on this convex suture manifold. And first of all, I think what you were saying is written down by Colin Gijini Honda in one of their ECH equals Hager-Fleur papers. Are you asking for like a different proof using this picture, or?
Oh, I was thinking it's like very reminiscent
Mhm.
of that picture.
Yeah, so I think in their picture they use the open book decomposition. Well, but it is the same picture. If you take out a ball and turn it into convex, then it is the sutured ECH. And it is also the hat version. Yeah, then.
Okay, thank you.
Mhm.
Okay, well, it seems like we had a good set of questions. So let's thank our speaker again.